this area right there, we get a smoother range of what's going on. And the non-uniform weights corresponds to this assumption that the more nearby a pixel is, the more weight it should have. So, question. If you're going to do the moving average computation, the number of weights that you have should be what? A, odd, because it's easier to have a middle pixel. B, even. That way it can be symmetric around me. Or C, obviously either even or odd. For most of us, we tend to use odd-sized sets of weights. And what that lets me do is put my set of weights centered over the pixel that I'm changing. Right? Otherwise, what I have to do is sort of put the center between the set of weights and average them that way. And so we tend to use a odd but symmetric weight mask.
All right, let's talk about comparing filter results. I took a vector of 10 random integers and plotted them as a line plot. I then filtered the vector with a uniform filter of length 5 and plotted the results. I also did the same with a non-uniform weighted filter. Can you figure out which is which? Type in the filter that you think produced the line plot in the corresponding box. Use the same notation as you would to write a vector in Octave or MATLAB, that is, including the 2 square brackets. For the original set of numbers, you can type in the word original. The blue line has the biggest extremes. It's got to be the original. The green line is smoother, but has some uncharacteristic segments. For instance, here. While the original sequence decreased significantly, the green line actually increased a little. Similarly here, the original sequence increased, but the green line dipped. This indicates that values other than the central value at each point are affecting the results too much. Looking at the first unusual spike, it seems that the peaks on both sides are contributing as much as the central value. The green line is a result of applying the uniform filter. The pink line is also smooth, but more importantly, its peaks and troughs are well aligned with the original. This seems to indicate that the central value had more weightage compared to the neighboring values. So yes, the pink line is a result of applying the center-weighted filter. One minor detail: when applying these filters, we would want to scale the weight so that they sum to 1. For the uniform filter, this would be dividing by 5. And for the non-uniform filter, we'd divide by 16.
So what about images? Well, images are two-dimensional, and doing this in 2D is pretty straightforward extension of 1D with a little bit of a flip. That's going to be a joke. All right. So let's do a moving average in 2D. I hope you can see that there's a whole bunch of zeros in this picture over here. You see all those zeros? And then in the middle, in the bright area, are these 90s. So this maybe is an image that goes from 0 to 100 or whatever. But the idea is that zeros are dark and 90s are bright. And what I'm going to do is I'm going to take a moving average. So here I have my little average, right? It's a 3 by 3 average. And I'm going to take the middle pixel over here and I'm going to put that average over there. Okay? So if I put my average over all zeros and I take an average of all zeros, I get, Megan, what's the average of all zeros?
0.
Every now and then I'm going to ask her some questions. She has no idea what the answer is, and she's not even sure whether she's supposed to know the answer, so that's kind of cool. Okay, it's 0. So now we move our square over 1, right? So we move it over here, and we get 0, 0, 0, 0, 0, 0, 0, 0, 90. Okay? What's the average of that going to be? Well, you can think of each of these as being 1/9. So 1/9 times 0 summed up 8 times plus 90. That average is going to be 10. Okay, so it turns 10. And then I slide it over 1 more, and now I get 2 90s, so its average is going to be what? 20. And keep going, I get 30, and keep going further, 30. So I'm just moving this along, replacing the average. And finally, I get this total averaged value, right? And you can see that by putting a 3 by 3, I get this nice bright area right around here, which is where my 3 by 3 can sit over all the 90 values. And everywhere else, it sort of falls off. And you'll notice these are zeros here until we get to these 10s. Where do those 10s come from? They come from this one little bright spot there, okay? And one of the things, by the way, you may have noticed is by the boundaries, we get these kind of dark values. And we're going to talk more about boundary conditions in a minute. All right. So the math of what we just did is referred to as correlation or correlation filtering. And what we just did is we did it with uniform weights. So let's assume that our averaging window is size 2k plus 1 by 2k plus 1. So remember, it's odd, right? So if k were 3, that would be a 7 by 7. If k was 1, that'd be a 3 by 3, right? So we have odd-sized windows. So what we do is we're going to loop over all of our pixels around some location f of ij being the row and column, and we loop over all the u's and all the v's going from minus k to plus k, summing up all of the pixels. And then, since we have a uniform weight, right, so you have a weight of 1 there, we divide the whole thing by the number of weights in the filter, right? So if I had a 3 by 3, that would be 9, so k was 1, 2, 3, yep, it'd be 1/9. But that was uniform weights. And I don't know about you, but I don't look any good in a uniform anymore, so we're going to do something totally different here. No, all we're going to do is we're going to do what are called non-uniform weights. And what that means is instead of having 1 over 2k plus 1 squared, we're going to have a different weight at each location. And so these non-uniform weights are written here as h of uv. And those are simply the weights that you're going to still sum over the whole thing, but now these different weights are going to be applied as you move around inside that mask. This operation is referred to as correlation or the cross correlation, and if written as here, we would say that G was the correlation or cross correlation of H with F. So, this H, by the way, is referred to by many things, okay? It's called a kernel, it's called the mask, it's called the coefficients. It is just the matrix of the linear weights that get used. By the way, in case any of you have taken a machine learning class and you've talked about machine learning kernels and the kernel trick, there's a very, very slight relation here, but really it's a totally different thing. We're thinking about these kernels as these masks that we do the computation. So then the question arises, what makes a good kernel? Well, obviously, a very successful major. That was a joke. So let's consider a uniform filter. Did you get that one, Megan? Yes, you got it. Good. All right, so remember the averaging filter, right? So the averaging filter was just this box filter of all 1/9, and as we moved it around, we took this image on the left and we created this image on the right. All right, so the question naturally arises, what if I have some image like this and I apply that box filter? What would I get? Well, I would get this. And that is known as really, really ugly. Okay? That does not look, at least not to me, as a nice smooth version of the original. Now, if you're looking at an itty-bitty monitor, it might look nice, but trust me, it's really ugly. And the question is, what went wrong? Well, really what went wrong is squares are not smooth, which is probably a statement from the 60s, but it's what I mean. Basically, filtering with something that's not smooth to try to think about blurring or filtering an image to make it smoother doesn't seem right. And in fact, we'll be able to say a lot more about what smooth means in terms of the mathematics in a few more lectures when we talk about Fourier analysis. So what was the problem? To get a sense of what's wrong, imagine that you had a single point of light that you were looking at very far away, right? And you blurred the camera so it was out of focus. What would the image look like? Well, it would look something like that, okay? Brighter in the middle, falling off towards blackness at the edges. Very, very deep, all right? And in fact, if we think of images as functions, I could take this image and I could plot it as this function. If I plotted that blurry spot, what kind of function would I get? Well, it would look something like here on the right. Thinking about this, if we wanted to blur a single pixel into a blurry spot, we would need to filter that spot with what? Is it A, 3 by 3 uniform weights? Is it B, an 11 by 11 square of uniform weights? C is something that looks like that blurry spot. Could we use a 3 by 3 uniform weights? No, we did that and it looked awful. How about an 11 by 11 square of uniform weights? That would be better, right? Because it's bigger. Well, sort of yes, sort of no. You still have this problem that you get these very hard boundaries. Clearly what you want is something that looks like that blurry spot. Higher values in the middle, lower at the edges. So what would such a function look like? Well, it would look something like this, and it would be what's referred to as a Gaussian filter. So here's our original image. Here is our filter. Now, this is not a great Gaussian because it's only 3 by 3, but you'll notice it's higher in the middle and then falls off at the edges and even falls off more at the corners. And what that is that's a very sort of low representation, very coarse representation of a Gaussian function. And our Gaussian function is written here. This is the two-dimensional Gaussian in the UV, 1 over 2 pi sigma squared, e to the minus u squared plus v squared over sigma squared. That's a circularly symmetric Gaussian function. Get to know and love your circularly symmetric Gaussian functions. All right? So here I have, that's in fact what that plot was. So we're going to do smoothing proportional to this exponential e to the minus x squared plus y squared over 2 sigma squared. And the technical description of this is that it's a circularly symmetric fuzzy blob. That's what the Gaussian is going to be. So if we take that image, that same high textured image that we had before, and we filter that with this now Gaussian blurring function, what are we going to get? We get something that looks, like that. So much better, so much nicer, right? I mean, compare smoothing with a Gaussian to the non-Gaussian. Gaussian, non-Gaussian, right? And you can see the difference. In fact, in the non-Gaussian, you see all these sharp edges. Now you really see them because they're red, all right? But when you do it with the Gaussian, you get that nice smooth blurring. Okay, so now we're going to get to a quiz that's actually hard. It's not really hard. It just kind of feels hard because I always screw it up. And that is, the Gaussian filter that we're talking about is referred to as a exponential. And the complete formula here is what? So h of uv is, by the way, you see the exponents? They're the same everywhere. The only thing we're looking at is the constant. So the question is, what's the right constant? 1 over 2 pi sigma squared, 1 over the square root of 2 pi sigma squared, 1 over the square root of 2 pi sigma. Okay? Going back to here, it's just 2 pi sigma squared. I always forget where everything falls. Those of you who know your normal distributions, you'll remember that that's the constant that's in front of the Gaussian. So the Gaussian we just talked about is what's referred to as isotropic, a fancy word for circularly symmetric. And so it basically had one parameter, just sigma. Right? Bigger sigma is, the more the blur. But we have to implement these in digital computers. We actually have to have a matrix. And so then we have to worry about two things. The size of the matrix. Is the matrix 3 by 3, 5 by 5, 11 by 11? And then the sigma that's represented within that. So let me show you that first. In Gaussian filters, we talk about the variance, sigma squared, or the standard deviation of sigma, and that's the amount of smoothing. So these two filters are the same size. They're both 30 by 30s, but the sigma inside one of them is 2. The sigma inside the other one is 5. So the 5 has a larger sigma. Now, sometimes we'll make a mistake and say it's a larger kernel. When we say larger, what we're actually talking about is the size of the sigma inside. And we can distinguish that. So here's an example of the size of the kernel. So both of these kernels have a sigma of 5, but one of them is represented within a 10 by 10, and the other is represented within a 30 by 30. Which one do you think is going to work better? The bigger one. It's smoother. It's going to work better. Okay? And by the way, if somebody says, oh, I smooth that with a bigger kernel, they actually mean a bigger sigma. That's what you care about, is the size of the sigma, not the actual kernel. The kernel has to be big enough, and then the sigma is within that. As I mentioned at the start of this class, I'll be showing my examples mostly using MATLAB. I know we've looked at the course developer, Arpan has worked on being able to do it in Octave or also in Python using various image manipulation, OpenCV. But what I'm going to do is show you filtering in MATLAB. And basically, MATLAB makes it trivial to build filters and apply filters. So in MATLAB, what we're going to do is we're going to define two things. We're going to define the size of the kernel. Remember, that's what we talked about before. So in this case, it's going to be a 31 by 31. Again, odd, so I can put a center pixel down. I'm going to have a sigma of 5. And MATLAB has this really great little function called fspecial. And obviously it's special, or they would call it something else. In fspecial, you can give it parameters, one of which is the type of filter you'd like. You can give it the size and the sigma. You can also give it rectangular size and multiple sigmas. It will build these filters for you. And in fact, MATLAB has this beautiful little function called surf, right, which will plot for you as a surface. And if you do it with the right color map, you would see this. You can also show it as an image. That's what this little picture is right here. All right. But even more importantly, you can take your image, and that's our image here of a panda. I can filter it by this H, which was the filter we just built, and then I can show that what's that going to look like? It's going to be a blurry panda. Okay? This code